Hi all, welcome to this next lecture of the course Concentration Inequalities. This lecture will be about describing the Kramer-Chernoff method for obtaining concentration inequalities, which is probably the simplest and most well-known, one of the most well-known methods for controlling the tail of random variables. And we'll also see some examples to illustrate concrete applications of this method. So let's start by recalling Markov's inequality, which you may have seen in a basic probability class. So this inequality basically says that if you have a non-negative random variable x and any number, let's say epsilon greater than 0, then the probability that x is larger than epsilon is bounded by its expected value over epsilon. Okay, so this is Markov's inequality. Okay, just before we proceed, it's worth looking at a quick proof of this inequality. So this just comes about by writing down the formula for the expectation. So let's just do the proof in the special case that x has a density function. The general case is simple enough, simple in analogy. So this is the integral of x versus the density function of x dx on the entire real line. We split this in two parts. Since x is non-negative, we can first integrate from 0 to epsilon and then integrate from epsilon to infinity. Okay, so this part is bounded below by 0 trivially, and this part x is always larger than epsilon. So we have that you can bound this sum from below by epsilon times the integral from epsilon to infinity of fx of x dx, which is simply epsilon times the probability that x is larger than epsilon. Okay. So having seen Markov's inequality, a very simple but insightful observation is that the technique used to derive Markov's inequality can be applied to any non-negative, non-decreasing function phi of an arbitrary random variable x. So x here does not need to be non-negative, whereas in Markov's inequality you needed x to be non-negative, and this happens the following way. So if you are interested in finding the probability that x exceeds epsilon, this event implies that phi of x is at least phi of epsilon. Okay, this is because phi is non-decreasing, and further Markov's inequality can be applied here to give an upper bound of expected value phi of x divided by phi of epsilon. Okay, so this holds for any random variable x provided you take an appropriate function phi which is non-negative and non-decreasing. So the second inequality holds because phi is non-negative, and then by Markov's inequality. Okay, so for example, if we choose y to be modulus of x, okay, and phi of y equal to y or y square or y cube or y raised to 4, notice that phi is non-negative and non-decreasing on y which is non-negative. Okay, so as long as y is non-negative, which it is in this case, phi of y is indeed a non-negative non-decreasing function, and you could think of applying this method to y to give you a family of tail bounds for the random variable mod of x depending on its higher order moments. So you would get on the right hand side, you would get things like expected value of y, or expected value of y square, or expected value of y cube, or expected value of y raised to 4, which can be thought of as the family of higher order moments of x. Okay, So you can get an entire collection of inequalities for the same event, which is the probability of x exceeding epsilon. Okay, so one could presumably think of trying to find the tightest such inequality, and this is where the Chernoff bound comes handy. One way to think about the Chernoff bound is that it basically does this whole family of inequalities depending on different moments by taking a single function that captures all the moments. Okay, so you may have seen this concept of a moment generating function, which is this function phi x equal to e raised to lambda x, let's say for any lambda greater than equal to 0. This function phi of x when lambda is greater than equal to 0 is a non-decreasing and non-negative function, and when you substitute a random variable for x and take the expectation, it becomes what is called the moment generating function. Okay, so really the spirit of the Chernoff bound is to try and replicate what one would do by applying repeatedly Markov's inequality with different polynomial functions phi, and instead of that take a single function which is like the mixture of several polynomials with infinite degree, which is the exponential function. Okay, so that's where Chernoff's bound usually comes in. This is one way to approach the derivation of the Chernoff bound. So as such, the derivation is very simple. So let's take phi of x equal to e raised to lambda x, where lambda is any non-negative number, so that phi of x becomes a valid non-negative non-increasing function. And for any random variable x and any number t, we can have the following derivation. The probability that x exceeds t is the same as the probability that phi of x exceeds phi of t. This is because phi is as we just saw, phi is non-decreasing, okay, with an increase in its argument. And once we have p of phi x greater than equal to phi of t, by Markov's inequality we can upper bound this by expected value of phi of x divided by phi of t, which we can write as follows: e raised to minus lambda t, which is the denominator, into expected value of e raised to lambda x. Okay, this is by Markov's inequality. Now let's bring all terms into an exponent form by writing as follows: this is equal to the exponent of negative of lambda t minus the logarithm of expected value of e raised to lambda x, and this new function, which is the logarithm of the moment generating function, we will find it convenient to denote it by phi x cx of lambda. Okay, and so finally we get the bound e raised to negative of lambda t minus cx of lambda. Okay. Okay, now notice that when we did this derivation, all that we needed was to choose a lambda which is greater than or equal to 0, and you get, for every favorite choice of lambda, you get a bound on the right hand side. Okay, for the same event x greater than equal to t. So since this holds for all lambda non-negative, we can optimize the right hand side above here, okay, which is this thing highlighted. You can think of optimizing this over all possible choices of lambda greater than equal to 0 to get the tightest possible bound. Okay, so by this what I mean is that it also holds that probability x greater than equal to t is less than equal to the infimum over all lambda greater than equal to 0 of e raised to minus lambda t minus cx of lambda. And you can easily move the infimum. Think of infimum, if you have not seen this before, as a minimum modulo a technicality. Okay, so infimum is really like a minimum. It allows you to take minimums over sets where the minimum may not be exactly attained. So it follows that this is exactly the same as the exp, and when you move the infimum inside the exponent with a minus sign, you basically get a supremum over all lambda greater than or equal to 0 of the function lambda t minus cx of lambda. Okay, so you get what looks like an exponentially decaying tail bound for the probability of x exceeding a level t. Okay, which has itself the interesting property that the bound itself is the solution to an optimization problem. Okay, so what's in the exponent is the solution to an optimization problem, which we will denote as cx star as a function of t. Note that lambda is no longer an argument of cx star because it has been optimized out. Okay, so e raised to minus cx star of t is by this method the best possible, the tightest possible bound for the probability of x exceeding t, and this is what is called the Chernoff bound. Okay, so the Chernoff bound, to summarize, is that the probability that x exceeds t is at most e raised to minus cx star of t. Okay, let me highlight it here so that it's easy to remember. Okay, so the moment you can find, depending on the random variable x, its associated function cx star as a function of any argument t, you can immediately enjoy the liberty of putting down bounds, upper bounds on the tail probability of x exceeding t. So a couple of remarks here. There's an equivalent form for the same Chernoff bound, which is obtained by setting the right hand side of the Chernoff bound equal to a number delta. Okay, so if you set the right hand side equal to delta and invert this expression, you get that the right t that you have to put is something like this. So the probability that x is larger than cx star inverse of log 1 by delta is less than or equal to delta. So we will often use this form, this equivalent form for concentration inequalities, where the tail probability is constrained to a certain delta, which is this delta on the right, and we want to equivalently find the level at which the tail probability of x falls to delta or below. Okay, and this you can also call this as the delta quantile of x, or the 1 minus delta quantile of x. This name is common in statistics and probability. The second remark here is that cx of lambda, which we defined in our derivation of the Chernoff bound to be the log of expected value of e raised to lambda x, is often called the cumulant generating function. Okay, it's of course obviously the log moment generating function of x evaluated at lambda. The third remark is that this function, which is derived from cx, which is called cx star, by solving an optimization problem involving cx, is often called the Kramer transform of x. Okay, so if x is a random variable and you happen to evaluate cx star, this function is called the Kramer transform of the entire random variable x. Okay, so if you have a random variable x on a probability space, or equivalently if you have a measure on a probability space, then you automatically have a Kramer transform. Okay, and we will see that this Kramer transform function cx star for any random variable x is a very important object to study and think about if we want to prove clean or if we want to give clean or usable concentration inequalities for tail probabilities of random variables. Okay, we will move forward to list down some properties of these functions that we have introduced, the cumulant generating function as well as the Kramer transform function of x. So So we'll start by making the assumption that suppose there exists a positive lambda such that the cumulant generating function is finite, okay, of x. Okay, so that just means that the cumulant generating function of x is not trivially infinity everywhere, depending on any lambda. That's not the case. So there exists at least one lambda for which Cx of lambda is finite. Let B be the largest possible or the supremum of all such lambda for which the function Cx is finite. Okay. We have then that Cx is infinitely differentiable over the interval 0 to b. This is not very surprising because if you look at the definition of Cx, it is the log of the expected value of e raised to lambda x, and wherever this is finite, we often know that the exponential is a very well behaved function in its domain of convergence, and it can be differentiated and integrated infinitely often. So, Cx of lambda just inherits the smoothness properties of the exponential function. Okay, you can think of it as in that way. The last property is that Cx is actually a convex function in 0 to b. Okay, so Cx is always a convex function, and in fact it is strictly convex if x is not a constant random variable. So if x is anything other than a trivial or an unchanging random variable, then you get a strictly convex function Cx. Okay, so why is this? Let's quickly show why this convexity property holds. So if you write down, so let's take theta between 0 and 1. Let's take any number theta between 0 and 1, and lambda 1 and lambda 2 in this valid interval 0 to b. Let's write down Cx of theta times lambda 1 plus 1 minus theta times lambda 2. We will often find it convenient to write 1 minus theta with the symbol theta bar. So by definition, this is the log moment generating function of x evaluated at theta lambda 1 plus 1 minus theta lambda 2. Okay. So one can write this as log of the expected value of a product of e raised to theta lambda 1 x into e raised to theta lambda 2 x. Okay. Now we will apply a very standard result, a standard inequality which you may have seen before, called Holder's inequality, to get so the log is the same outside. Holder's inequality helps us to bound an expected value of a product like this, and in this case you get expected value of e raised to lambda 1 x, okay, the whole raised to theta. So this is the expectation being raised to theta, and on the other hand you get e raised to expected value of e raised to lambda 2 x, the whole thing being raised to theta bar, which is 1 minus theta. Okay, so this is by using what is called Holder's inequality. Okay, you can also interpret it as coming from a much simpler inequality called Jensen's inequality, which is really the definition of convexity. So just to give you a quick idea, you can look this up separately, but Holder's inequality says the following. So there are several ways of writing Holder's inequality. If you have two numbers p and q such that, so let's say if 1 by p plus 1 by q equal to 1, and you have any two random variables x and y, the expected value of xy is upper bounded by the expected value of so in fact I can put modulus signs here. to make all of these quantities and random variables non-negative. So expected value of x raised to p, the entire thing raised to 1 over p, and similarly expected value of y raised to q 1 by q. Okay, so apply this here with p being equal to 1 over with p being equal to 1 over theta and q being equal to 1 over theta bar. Okay, so that the conditions of the inequality are satisfied, and you'll see that this is Holder's inequality. By the way, if p and q are equal to half in Holder's inequality, you get what is called the very well known Cauchy-Schwarz inequality. So Holder's inequality is just a generalization of Cauchy-Schwarz, which you may be much more familiar with. And so the moment you have Holder's inequality here, this just simplifies to theta cx of lambda 1 plus theta bar cx of lambda 2. Okay, and so this is why cx is convex. Okay, this is exactly this left hand side here less than equal, being less than this right hand side here is why is the definition of cx being convex. Okay, now we want to argue that there is strict convexity, which means that the inequality here is always strict. Okay, in if x is non-trivial. So this is also easy to show. So with equality, if and only if. So it turns out that in Holder's inequality, which I have written down here, the inequality is an equality. So this inequality is an equality if and only if x and y are scalar multiples of each other. Okay, so the random variables x and y are exactly related by scalar multiplication. So if you translate that requirement here, it means that the random variable e raised to lambda 1 x has to be a scalar multiple of e raised to lambda 2 x, okay, with probability 1 almost surely. Okay, and this is if and only if you take logs on both sides, lambda 1 x is equal to lambda 2 x plus some log alpha, which is another constant almost surely, and this is equivalent to x being a constant. Okay, so the only way that equality holds is if x equal to constant. So if x is not a constant random variable, then you will always have strict inequality, okay, inherited from Holder's inequality. So let me make some space here. The next point here is that Cx is always Cx star is always convex on its domain. Okay, domain is wherever it is finite. If it's infinite, we don't bother with talking about convexity. Okay, why is this? Why is Cx star convex? The reason is actually very simple. So if you look at the definition of Cx star here, okay, right here, it basically means, so how is Cx star of t computed? You basically take several possible lambdas and you compute this quantity, and then you take the maximum of all these. Okay, so for each fixed lambda, the function here as a function of t is actually just a linear function. Okay, so the dependence on t is just linear. So you can think of Cx star as basically taking the upper envelope or the maximum of a bunch of linear functions, each linear function being indexed by lambda greater than or equal to 0. So Cx star is just the max of linear functions. Okay, Cx star is the max or the supremum technically of linear functions. Okay, and it's very easy to show that if you have two or more linear functions, if you take the max of them and form a new function, that's always going to be convex. Okay, you can just convince yourself about this. The next property about Cx star, which is the Kramer transform, is that it is always non-negative. It cannot be negative at all. This is because Cx, the log moment generating function, is 0 at 0. Okay, so if you go to the definition of Cx star again, if you plug in lambda equal to 0 here, then one feasible value for this optimization problem is equal to 0 minus Cx of 0, which is 0. So Cx star can only be larger than 0, it can never be smaller than 0. Okay, so Cx star is a non-negative function. Moreover, if the expected value of x exists, if x has finite mean, then Cx of lambda, the log moment generating function of lambda, by Jensen's inequality for the convex function e raised to lambda x, can easily be shown to be lower bounded by lambda times expected value of x. This is just by Jensen's inequality applied to the convex function taking x to e raised to lambda x. And so this means that lambda e raised to x minus Cx lambda is always upper bounded by 0. And so for every t that is larger than equal to expected value of x, and for every lambda less than equal to 0, okay, so recall that in the definition of Cx star we only took lambda greater than equal to 0, okay, but what happens if you take a lambda less than equal to 0? So if you take t larger than the mean and lambda negative, what happens is that lambda t minus Cx of lambda turns out to be upper bounded by lambda expected value of x minus Cx of lambda, and we know that this is less than equal to 0 by Jensen. So the upshot of this is that for any t larger than the mean, the Kramer transform of the random variable at t can as well be written as the supremum of the same objective function over all lambda rather than only lambda greater than equal to 0. Okay, so this is nice to remember. You don't need to take you don't need to restrict lambda to be greater than equal to 0 when you are evaluating the Kramer transform for t larger than e of x to the right of its mean, but you can actually just consider the computation of Cx star of t to be an unconstrained optimization problem. Okay, so this allows you to do much more cleaner calculations and solving of the optimization problem, okay, rather than operating with a constrained optimization problem. So by the way, this function, so if you give me any function Cx, if I define the following function, which is the sup over lambda in R, lambda t minus Cx of lambda, this function Cx star of t has a special meaning and a name in convex analysis. It is called what is called the Fenchel dual of Cx, or the Fenchel-Legendre dual of Cx. So Cx and Cx star enjoy some very nice duality properties. Okay, so there is a whole rich theory of duality built on these foundations of functions and their Fenchel-Legendre duals. Okay, so the Kramer transform is essentially the Fenchel dual function of Cx, is what we've shown here. So we'll stop here and then we'll continue with applying this Chernoff bound technique to various random variables that we are familiar with.